everyone, this is PrachiGupta. Let's start with a new collab, that is C4 JAX deep learning tutorial. So first let's go through what is introduction to the JAX. What is JAX? JAX is a high performance numerical computing library developed by Google that combines NumPy like API, automatic differentiation, JIT compilation, vectorization, parallelization, all these functions it provides us, which are developed by Google. So let's see JEX functional programming. How does it actually works? So JEX embraces pure functions such that it always produces same output for the same input. Also, it has no side effect. It don't modify the external state. This enables powerful function transformations like grad, JIT, VMAP that we will see in the coming uh, videos. So let's start with the JAX. So first we will import the library that is required for, we will install the libraries that we will require. Once while the installation is doing, I'll explain you what is happening in the next cells. So here we are importing the JEX library, import JEX. Also we are importing jex.numpy as JNP. This is JEX version of NumPy, usually imported as JNP. So you don't need to import NumPy separately. You can import jex.np as JNP and you can use all the NumPy functionalities. Also we will use the key JSX transformations that we will see in coming videos, and then we'll employ the import the standard numpy. So here the installation is done. We will run this importing and we will see the version. So JEX version is also installed. We are checking the jex.devices and which is the current device, and the default backend is CPU. So this is what we have seen. Now, in JEX, tensors are called array, similar to NumPy's ND array. So they are fundamental data structures for all the computations. So what is a tensor? Tensor is basically a multi-dimensional array of numbers. So it can be zero dimensional, one dimensional, two dimensional, three dimensional, that we have already seen. Now creating arrays. How do we create arrays in JNP? So we just simply give jnp.array. It's similar to how we did in NumPy, how we did in Tensor. It's just the naming convention has changed to array. So jnp.array is used to create the array, uh, and it will be created in the array in the similar way. We have the scalar zero dimensional array, the shape and dimensions, all the thing will be same. You just have to do scalar dot shape, scalar dot and dimension, and you will be able to see the shape and dimension. I'll just run this. Yeah, we can see. Similarly we will do for the one dimensional array. We can see it for two dimensional array. We can see the array printed and the shape. For three dimension we can see the array and the shape. Now how to create special arrays? The similar zeros and ones arrays that we have seen earlier in the numpy, the same we are creating here with jnp.zeros and jnp.nums. Once I'll just play it, we can see these zeros and ones are created. We have seen the full also. So jnp.full is used to create a full array here. jnp.I again is used to create the identity matrix. Arrange we have seen, line space we have already seen in numpy and tensor. The same thing is done here with jnp.arrange and jnp.linespace. Now moving towards the random arrays. In numpy we used to define the random arrays differently. Here we use something different. So JEX requires a explicit random key for a reproducibility. Unlike NumPy, there is no global random state to make it pure. So we in NumPy we used to initialize random seed as 42, but here what we are doing, we will create a key, that is prng key. So I'll just create it. Just give me a second. So the we can see here prng is pseudo random number generator. So unlike NumPy and Torch, JAX uses this explicit PRNG keys to define the random number generation. So what we do, how we do it, we will do random dot PRNG key, and we will store it in a key, and then to generate a new random numbers, we must split the key. Key is the source and subkey is used for the actual operation. So we will split the key for each use. Whenever we are using it, we have to split it and use the subkey for a new use. So what we will do, random dot split key into key and subkey, and this is the subkey that we are going to use now to create a random array. How we will generate a random? So we will do random uniform subkey. We are passing the subkey here and the shape. So this is how we create a random array using the J6 PRNG keys. Now see, again here we are creating one more table. So I am again creating a subkey and we are using it. I'll just run it. So this is how it's created. It's again the same code. Okay, so why we need different keys? So let's try giving the same key and storing it in key 1 and key 2. So we have given the same keys here, and we will print key 1 and key 2. And for key 3 we are passing something else, and then we are trying to print it. So if you see, k1 and k2 have created same array, while the different seed has created a different array. So that is why it's very important to remember that the same key equals to same random numbers, that is reproducible. So that's why it is very important to keep the keys separate and use it. So coming to data types, the data types are similar to the what we have seen earlier. So again, we have int 32 64, float 16 32, and float 64, and we will just simply print it to see. Here again we have array.dtype to see the data type of the arrays. We can do the type conversions here as well. So suppose we have defined an array and if we wanted to convert it to int, so we have to do array name dot s type, and then we have to give the type that we want to convert. So this is how the converting works here. We can see original, int and float. Now coming to array attributes, we have shape, dimension, size, dtype, device, the same thing. Array dot shape, array dot end dimension, size, dtype and devices that we used to see earlier. Indexing and slicing again are same. There is no change in the indexing and slicing thing. So I'll just run it simply. You can see array 0 0 1 2 minus 1, it's all same what we used to get earlier. So I'll just simply run this slicing as well. So there is no change in the slicing. We will see the boolean indexing. It's again the same true false indexing that we have seen earlier. Arrays, so one thing, JAX arrays are immutable. So important difference from NumPy, JAX arrays cannot be modified in place. NumPy we used to do that, but in JAX we can't do that. So if we have defined an array, and if we would suppose, I'll just comment this 3 lines. I'll just uncomment this line. If I'll run, so suppose here I am trying to modify the defined array and I'll run it. So I'll get an error that I can't define it, change it. It is immutable. So we can't change it. But if we want to change the position, we have to use at and set to create a new array with the updated value. So what it will do, it will create, we will select the existing array dot at 0 the position, set the value, and it will create a new copy array with the updated value, and the original array will remain same. So if you run this, the original array is same, the modified array is this. So I'll just, if you want to set anything at a particular index or any particular slice, you want to add anything, you want to multiply anything at a particular location, you want to set anything at a particular location, you can use the add operation. And this is how it works. Now tensor operations, element wise operation. If we want to do the arithmetic operations, this will work same as it used to do earlier. There is no change. Similarly, we can add, multiply, divide, do everything, it will be same. For multiplication also, also the mathematical functions like sine, cosine, exponential, logarithmic, it's all same, there is no change in it. You just have to give exponential, jnp and the array and it will work. Broadcasting allows operation between arrays of different shapes. So how does broadcasting works here? The similar broadcasting rules are here that we have seen earlier, that they have to be compatible in the when dimensions are equal or one is one, and array have different n dimension, then prepend the ones to the smaller shape, and result shape is maximum along the each dimension. So if we want to add a scalar to an array, how it happens, let's see. 1 2 3, we want to add 10, so it will be 11 12 13. So this is how it works. How we add vector and matrix, it works the same as it used to do in tensors. Here if we want to print the matrix, the column, the result, everything works here. So it is again the same thing. We have defined an array, we have defined another array, and if we run this, we will get the multiplication. Reduction operation, again it's same, we have to just pass jnp dot sum, mean, mix, medium, whatever we want, we can easily get it. It will give the sum of the elements, mean, minimum, max, everything. If you want to the sum along some axis, you can pass the axis also. If you want to reduce rows, you can give the axis. If you want reduced columns, you can give the axis as 1. I'll just run it. Keep the dimensions. If you want to keep the dimensions, then you can like keep dimensions true, so it will not change the dimensions. Reshaping, we have already seen how to reshape. The similarly it will do, we just have to give the array and the array dot shape, and then to reshape we will do array dot reshape and it will reshape the array. I'll just run it. So this was our original array, we gave reshape 3 comma 4, so it reshaped it to this. We gave 2 3 2 2 3, so it reshaped it like this. So auto reshape also we are doing again here, the reshape. Flatten also works the same, flatten and revel. I'll just run it quickly, you can see the output. Transpose also it works the same, just give matrix dot t, it will transpose it. So basically array dot t, it will transpose it. If you want to expand the dimensionalities, you just have to pass the array expand dimensionality, the array which you want to expand the dimensionality, and the axis on which you want to expand it. So this is how it works. Squeeze we have already seen. Similarly the functionality is same, only the color is changed. Here we are using jnp. Concatenating and stacking also, the logic behind is same, the only thing is here we are doing jnp dot concatenate and here we are doing stack dot jnp dot stack. So I'll just quickly run this. You can see a and b concatenated, and along with x is 0 and along with x is 1. I'll run this also. So this is the stack, and this is the vertical stacking, and this is the horizontal stacking that we have done. Now, in the next video we will see the linear algebras for deep learning. um, that's all for today. Thank you so much.